Alright, so we're taking a look at section 1.2 notes today, factoring polynomials using the remainder theorem and the factor theorem. So first things first, we're going to do these warm-up questions, which are a basic grade 10 review of factoring. So let you go ahead and try those, and I will show you the answers in just a moment over here. Alright, so once you've done that warm-up, these are the answers you'll be getting. So the first and the second questions are simple trinomials with a GCF in the second one, and the third one is just a difference of squares. Okay, now we can move on to what we're going to be learning today. So let's take a look at the first part of our lesson here. So the first part we're going to look at is this sentence over here. How do we know if a given binomial of the form x minus a is a factor of polynomial p of x? So when we're dividing a polynomial p of x by a factor of x minus a, well, we learned yesterday that this is going to be a factor of p of x if when we divide p of x by x minus a, we get a remainder of 0. So when p of x is divided by x minus a and the remainder is 0, that's when we know that x minus a is a factor of p of x. So our goal today is going to be using this idea and using other concepts to try and figure out when something is a factor of a polynomial without having to do the entire long division or synthetic division on it. So with that in mind, let's move on to our first example here. So for each of the polynomials below, determine whether the given binomial of the form x minus a is a factor. Also evaluate each polynomial by substituting x equals a. So on the left hand side, we're going to do synthetic division to try and figure out what the remainder is. On the right hand side, what I need you to do is take this value x equals 1 and plug it into the polynomial and see what does that work out to. So I'm going to let you go ahead and try that, and once you've done that, we will. Alright, so once you have done the two steps over there, what you'll notice is that, for example number 1, when we do synthetic division, we actually get a remainder of 0. However, when we plug the 1 into that same polynomial to evaluate it, we also end up getting a result of 0. I notice the same pattern in the second example. When I do the division by 3, I get a remainder of 4. And in fact, when I substitute the 3 back into the expression, I still get an answer of 4. So what this means is there must be a relationship between the remainder and me evaluating that expression by plugging in that remainder. So just to confirm that it works, let's try and do that for the third example here as well. So I'll let you go ahead and try that and do it with the third example and see hopefully if you notice the same pattern again. Alright, so once you've done that again, you'll go ahead and verify to see that you get 0 and 0 in both cases. So if I go ahead and highlight what I did here, I plugged in -2 to try and evaluate that polynomial, and on this side I did the synthetic division with -2, and in both cases I ended up getting 0 as a final result. So that means there must be a relationship between the two different expressions over there, and in fact there is. So how can we tell whether a binomial is a factor without dividing? Well, we can actually go ahead and use this idea on the right. We can substitute the a value from x minus a into the polynomial p of x, and if the remainder is 0, then it's a factor. Alright, and in fact we can formalize that statement into something called the remainder theorem. The remainder theorem says is when a polynomial p of x is divided by a binomial x minus a, then the remainder is simply going to be the valuation of p of a. So if you take a, plug it into the polynomial p of x, whatever the answer is going to be, that's going to represent the remainder of that division. Also, a special case of the statement is when that remainder ends up equaling 0. And that's where we know that x minus a is actually a factor of the polynomial p of x. And we give this a special name, we call it the factor theorem. So remainder theorem says when you plug the a value into the polynomial, what you're going to get is going to be the remainder. And the factor theorem says when that remainder happens to be 0, then that means x minus a is a factor of the polynomial p of x. So now when we want to figure out if something is a factor or not a factor of a polynomial, we're going to go ahead and use the idea of factor theorem. We're going to plug in the a value into the polynomial, and if it gives us a 0, we know that that expression has a factor. If it doesn't give us a 0, then we know that it's not a factor. So let's go ahead and test some examples over here. I want to figure out if x minus 3 is a factor of that polynomial there. So to do that, I'm going to go ahead and use the remainder theorem, which means a value here is 3. So I want to evaluate what p of 3 is going to be. So let's go ahead and plug that in. I'm going to go 2 times 3 to the 4 minus 5 times 3 to the 3 minus 5 times 3 squared plus 5 times 3 and then plus the 3. So you work that out, and what you're going to end up getting is you're actually in fact going to end up getting 0. And you can go ahead and check that yourself, plug it in and see what you get. Alright, so what this is telling us that because when I plug in 3 into the polynomial, I get a remainder of 0. What this is telling me is that x minus 3 is a factor of 2x to the 4 minus 5x cubed minus 5x squared plus 5x plus 3. Similarly, I want you to go ahead and try and see if example number 5 is also in fact a factor. So pause your video right now, go ahead and try that, and then see what you come up with. Alright, once you've had a chance to do that, let's see if you were correct or if you weren't correct. So when you plug in a equals -2 into the polynomial, and we'll call it p of -2, you will in fact end up getting a remainder of 45. You're going to have 45 left over. So because the remainder is 45, we know that x plus 2 is actually not a factor of the polynomial. So the main reason why we're doing this is so we can eventually go ahead and factor polynomials that are as complicated as something like this, and be able to do that in a very systematic and organized manner. So one of the beginning points is going to be to figure out if something is a factor of that expression or not. Let's take a look at our next example. Here I want to go ahead and use the factor theorem to try and test to see which one of these expressions is in fact going to be a factor of that polynomial. So I'm going to let you go ahead and do that. So test each and every single one of them using the remainder theorem and the factor theorem, and then we're going to identify which one of those are in fact factors or not. So pause your video here again, give that a try, and then I will load up the answer in the next slide. Alright, so once you've done that, you'll notice that we end up getting a remainder of 36 for the first one, 0, 0, and 0 for the rest of the three terms. So what this tells us is that this is not a factor, and this is a factor, and this is also a factor. And what that means is, since my polynomial was a cubic and I've already got the three factors, so what this means is this polynomial can be factored exactly into the following three factors: x minus 2, x minus 1, and x plus 5. And you can check that when you open those up, you should end up with the same polynomial up at the top. That was pretty cool. If we know what the factors are, we know what the polynomial is going to match up with it. But what if we could work backwards? What if we could work with this polynomial and then use this idea to try and figure out what the three factors are going to be? Because so far, we know how to factor a quadratic. We quite haven't figured out how to factor a cubic or a quartic or a quintic, functions of higher degree powers. Maybe we can use this strategy over here to try and figure out what these factors are going to be. Which brings us to the next part of our problem here. What do you notice about the constant term in each of the factors compared to the constant term of the original polynomial? So what I'm getting you to compare is I'm getting you to compare these terms over here, the constant term in each of the factors, compared to the constant term in the original polynomial. Take a moment, think about it. What do you notice about those terms 2, 1, and 5 compared to 10? And hopefully you will have realized that -2, -1, and +5 are all factors of 10. They're all factors of 10. 2, 1, and 5 are all factors of 10. And in fact, it's this step right here, it's this observation right here that gives us the information that we're looking for. And this is not a coincidence. This is in fact the result of something called the factor property. And here's what the factor property says. The factor property says if x minus a is a factor of a polynomial p of x, then the a value of each of those factors is going to be itself a factor of the constant term of the polynomial. So whenever you look at the factors of any given polynomial, the constant terms associated with each of the factors are themselves gonna be a factor of the constant term of the entire polynomial. That's gonna happen automatically for each and every single problem that we factor. This is very important to us. This is very important because this information, we can use it backwards to try and help us factor polynomials of higher degree. And to do that, we can simply start by looking at the constant term of the polynomial and ask ourselves, what are all the different factors? Write them down, and then test to see which one of those is going to be a factor of a polynomial, and as a result, I'll have the factors to my polynomial. A tedious way of doing it, but that's where we're going to start. So, very neat property. We saw what it does above in the example, and now we're going to use this property to figure out some other problems. So far we have learned the factor theorem, the remainder theorem, and the factor property. All three of those things are going to help us solve the big idea problem here, which is something like this. Our goal is to try and fully factor a cubic polynomial now. We've become really good at solving quadratic and degree 2 polynomials by using all the different factoring strategies that we know, but we haven't quite tackled the cubic yet. So using what we learned now and combining it with what we already know, we're going to try and tackle this problem and factor this cubic. So where do we begin? Well, first we need to find a factor of that polynomial. I could just try guess and check, but I still need some direction where to begin. So what I'm going to begin with is I'm going to begin with this constant term 6. I know from the factor property that whatever factors I do end up with, each of those constants is going to be a factor of this term 6. So let me work backwards. Let me start off by taking a look at this term 6 and writing down all the factors of 6. So factors of 6 are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. And here's the trick. I don't have to test every single one of those things. I don't have to test all 8 values over there. I just need to test enough values until I find one factor. Because once I've got one factor, then what's going to be left is a simpler quadratic which I can factor in other ways. So let me start by checking a few of these values. I'm going to start off by trying x equals 1. So when I try x equals 1, I'm going to plug x equals 1 into that polynomial and hope I get a remainder of 0. Let's try that. When I plug x equals 1, I'm going to get 2 times 1 cubed minus 9 times 1 squared plus 7 times 1 plus a 6. Do the math. You're going to get a remainder of 6. So I know x equals 1 or a value of 1 is not going to work. Let me try something else. Let me try negative 1. So when I try negative 1, I'm going to get 2 times negative 1 cubed minus 9 times a negative 1 squared plus a 7 times a negative 1 plus a 6. I plug that in and I will get a result of negative 12. If you want to pause the video and test that for yourself, please do that. Make sure that's what you get. So both 1 and negative 1 didn't work. I move on to the next trial and error. Let me try x equals 2. and hopefully we get one this time. So 2 times 2 cubed minus 9 times 2 squared plus 7 times 2 plus the 6 equals, and plug that in, and in fact we do end up getting a 0 this time. So what this means is, so this is telling us something very, very important. This is telling us that therefore x minus 2 is a factor of the given polynomial. Which means I can take that polynomial, I can write it as x minus 2 times by another function which is going to be a quadratic. So let me go ahead and figure out what that quadratic function is going to be. I'm now going to go ahead and use synthetic division to figure out the quotient for that. So use synthetic division. I'll start off with the original polynomial, and in fact what I'm doing is I want to use synthetic division to find the quotient of the division. Two x cubed minus 9x squared plus 7x plus 6 divided by x minus 2. I want to divide them and I want to figure out what's the quotient, because that's going to be the other factor. So let's do that. Do the synthetic division here. You get 2, negative 9, 7, and a 6. This is 2 here. 2, 4, negative 5, negative 10, negative 3, negative 6, 0. We knew there was going to be a remainder of 0 because we know that a value of 2 works. What we didn't know was the quotient that we get as a result of it. So now we know that this polynomial here, 2x cubed minus 9x squared plus the 7x plus the 6, can be rewritten as x minus 2 times 2x squared minus 5x minus 3, and of course there's a remainder of 0. So now I have factored that cubic into a linear function and a quadratic, and I'm almost there. Since this is a quadratic, I can further factor this. And to do that, I don't need any extra special skills. I don't need to go back and test the remainder of these values. I could if I really wanted to do that. The skills that I learned in grade 10, how to factor a quadratic, will suffice just fine right now, and I can go ahead and finish off this problem. So let's go ahead and factor that quadratic out, and I'll let you do that on the side. So you can pause the video, do that, and when you come back and you've done it, you will realize that the factors of that polynomial are going to end up being x minus 2, x minus 3, and 2x plus 1. So that's going to end up being the factored form of that polynomial. Please make sure you go ahead and test that for yourself. Make sure you get that. Alright, it's time for you to go ahead and try an example to see if you really make sense of this. So here's our next example. Pause the video, go ahead, give that a try, and once you are done that, you can come back and check your answer here. Let's go over the answer. We're going to start off by listing the constant term, which happens to be 2. And we're going to further list all the factors of 2. Lucky for you, I picked a small number, so there's not very many factors to test. We got plus or minus 1 and plus or minus 2. So we know that we don't have to try too many times until we find a factor. So let's start off with trying x equals 1. We plug in x equals 1 into our polynomial. 3 times 1 squared minus 4 times 1 minus 5 times 1 plus 2, and we end up with a remainder of negative 4. So that's not going to work. Let's try x equals negative 1. It's got to work. Plug in x equals negative 1. 3 times negative 1 cubed minus 4 times negative 1 squared minus 5 times the negative 1 plus a 2. And in fact, it does work. When you plug that in, you're going to end up getting a factor or a result of 0. That means we know that x plus 1 is a factor. This is where sometimes people get confused. I tried x minus 1, but my factor is always going to be x minus a. Since a was negative 1, x minus a minus 1 is going to give me x plus 1. Once I have one of the factors, I know that cubic divided by a linear function is going to give me a quadratic. And I can then go ahead and figure out the other two factors. So the next part is I'm going to divide 3x cubed minus 4x squared minus 5x plus 2 by x plus 1 to figure out what the quotient is. And I'm going to use synthetic division to do that again because it's quicker, makes things faster. Negative 4, negative 5, and 2, negative 1, 3, negative 3, negative 7, 7, 2, negative 2. 0, of course, I knew that was going to be 0. This tells me the polynomial. So therefore, my factors are now x plus 1 and 3x squared minus 7x plus a 2. You can go ahead and further factor this next part depending on how you learned how to do it. So x minus 6, x minus 1 divided by 3, which means you get x minus a half and x minus a third, x minus 2 and x minus a third. Gotta pay attention here. X minus 2 and 3x minus 1. So as a result, I now have the fully factored form. I can then say that the fully factored form of the polynomial 3x cubed minus 4x squared minus 5x plus 2 is actually x plus 1, x minus 2, and 3x minus 1. Here we go. So everything we've learned so far today, this is what we've learned it for, so we can go ahead and now factor polynomials of degree higher than 2. We could do the same thing with a quartic power 4 function or a quintic power 5 function using the same manner as well. This is the end of your notes for today. You're now ready to go ahead and tackle the problems assigned to you for your homework assignment. Good luck and have fun.